Alright, so I might just start off with why I'm doing a lecture rather than just handing in a report. So basically what you're going to see here is a whole bunch of movement, a whole bunch of non-intuitive experimentation, and a whole bunch of maths which you're not going to be able to grapple just by looking at it, or just by writing things down. And because the way the axes and positions and vectors are set up, I've decided to go with the lecture. I've decided to go with the practice so you can feel what's actually happening in the moment, because I think just reading off this paper, you're not going to fully understand what's actually happening. So, I might start off with the really basic stuff that we have already covered, and I'll build up from there. So, vectors and forces. If I have a linear force, right, so we're in deep space, there's no external forces acting on this, there's no gravity, it's not really relative to anything apart from myself. I don't have any gravity. And I push this with some velocity, say 1 meter a second, in this direction. I let go. It's going to continue on moving in said direction. We all agree. Now that doesn't matter about what axis I induce that force into. So it could be through this axis, it could be through this axis, or it could be through this axis. So I might just start by going over how we can actually spin things about an axis. So if I start with the wheel in front of me, and I have a in or out force, push or pull force on the right hand side of the wheel, and a push or pull force on the left hand side of the wheel, we get some resultant force of a torque about the y-axis. So in this whole demonstration, I'm setting up the y-axis to be up into the ceiling, relative to the ground, the x-axis to be left and right, relative to the ground, and the z-axis to be pointing through towards the door, towards you, and back into the whiteboard. So that's going to stay relative throughout the whole demonstration. So yeah, as I said, rotation about the y-axis is a push or pull on the left and right hand side. Rotation about the x-axis is going to be a push or pull on the top and bottom. As you can see, that's the line of symmetry. It's rotating about the x-axis. And then about the z-axis would just be me rotating the wheel. So an upwards or downwards force on the left and right hand side of this wheel. So, as I've explained, if we induce a linear acceleration, we're going to get a linear force, linear velocity, going in a straight path. And normally what happens is, if we have a particle and we have some other force intercepting this, or making contact with this to change its velocity, it's just going to be some sum of those two velocities. So if it's heading straight ahead, and I hit it, it's going to go off diagonally like that, right? But here comes the non-intuitive part, and the kind of whole point of this whole lecture. If we induce some rotation about the z-axis and some rotation about the y or x-axis, so long as you're rotating it about the z-axis and one other axis, something different happens. And what actually happens is there's a torque induced about the axis that you didn't initially apply the force into. So that's it in words, but what does that actually look like? So if I start by spinning this, and I hold it towards you, and what I'm going to do is I'm going to induce a force pushing towards you and into me. And this is going to be some impulse, and I'll explain what's happening in a minute. Right. Might give it some more angular momentum. So what's actually happening is, you see how it's rotating about the wrong axis. It should be rotating like this, right? If we apply the same logic as we did to the linear vectors, it should just be moving like that. But what we're seeing happen is some induced torque about what axis is this? About the second axis, sorry, I can't remember if that's X, Y, or Z. I'll put it in the report. So I might just get some of you to come up here and try this, because you might think that I'm actually, just doing this to it. But no, I'm actually not applying any force in this upwards or downwards direction. And so Danny, if you guys want to come up and try this. Yeah, sure. Alright, so I'll spin it for you.
Yeah.
Now,
And then just that, right?
yeah, but don't jolt it too hard, otherwise you're going to hit your own.
Yeah, yeah.
So I'll give some.
Wait, what? Oh, wait. That's actually really cool.
Yeah. Now try going the other way.
Whoa. I literally have to find it.
Yeah.
Wow.
It's very
That's so
non-intuitive, right? Does anyone else want to come up here and try it?
You should try it. It's cool.
Yeah, sure.
That's really cool.
It should just be moving in that direction pretty easily, shouldn't it?
Yeah, that's crazy.
Yeah. Gonna come?
Yeah, I'll try this.
Yeah. You think you can overpower the action, but you can't. You just can't stop this because this is physics. And I'm going to explain why this is happening. Yeah, it's fun to do.
Yeah.
And explain. yeah.
I can do it. I can overpower the force.
I used to do over a faster impulse. Okay. Yeah. Anyone else want to come up and try it? Yeah.
Hey, there's some pressure right now, Haley. Do you feel like you need to get up there?
That is so wrong. But
Yeah. Nice.
Oh, I just find it.
You want to come up? Alright. So, we now have no idea what's really happening, apart from there is some induced torque about the axis that we are not exerting some torque into. So, basically, we have lots of lecturers like to kind of skim over why this is happening. And what they're going to do is they're going to qualitatively tell you something called the right-hand rule, the right-hand grip rule, sorry. So, what we're going to look at is we're inducing some rotation about the z-axis, and very easily we're going to follow our right-hand grip rule. Actually, I'll make it around like this. So we're following that arc, we're following that curve, and our right thumb is going to stick out towards the door. So angular momentum is sticking through the axle, through the z-axis, which is rather non-intuitive. Then we're also going to have a look at the torque that we're exerting. So if we're pushing here and we're pulling here, that's going to rotate like that, and we're going to use the right-hand grip rule again, and we're going to follow that curve. Which means that if I'm spinning it like this, following with the thumb, and I'm turning like this, following the thumb, so the velocity, the vector of torque is up straight into the ceiling through the y-axis, and angular momentum is sticking through the z-axis. What we're going to find is that basically we can qualitatively say that the angular momentum is going to want to follow the direction of the torque. Right? So if I try this in practice, we now have angular momentum sticking out this way. We're going to push on this direction, pull on this direction, and we should see that the angular momentum wants to follow the torque. And that's what we see. So that's a pretty easy understanding of why this is actually happening. So angular momentum always wants to follow the torque. So what we can do is we can now set up an experiment where we can attach this wheel to demonstration. I've referenced this as the bicycle wheel experiment. And basically, we can use gravity to induce a torque about the this is hard to think of all the time. Yes, about the x-axis thing. And so what we should find is it's going to do something rather strange. Right. What on earth just happened? Right? That's my question. I'll rotate the other way. Who would think gyroscopes are stable? But how on earth does this actually work? I mean, right-hand rules is quite a bit arbitrary. Like, there's not really any reason to say, you know, by nature that this should follow the right-hand rule. That's just what scientists have come up with to try and define what's actually happening. So what is actually happening? Well, I'm going to have another try to explain this to you using some other bits of science. So, first of all, we need to understand, you might know this already, that I'm going to quote this from my thing. Force or acceleration, the direction that you see it moving in, is not necessarily the direction that it acts upon a system. So, I'm going to explain this with another example. So let's say, am I in front here? Let's say I have a car and it's rolling towards me. Now, I'm not very strong and I also don't want my car going into the ditch. So the car's coming towards me, it's coming towards me. And I'm stopping it, right? But it's much heavier than me, it has a much larger momentum, it has inertia, it has a much larger momentum. So it has a velocity, it's accelerating towards me. I'm applying a constant force against it, but it's still pushing me in the opposite direction. I'm not pulling the car towards me, I'm pushing it in the opposite direction. And eventually we'll get to a net zero velocity, but I will then overcome, I'm like chipping away at the momentum of the car, you could almost think, by constantly applying that force. I end up overcoming the momentum of the car, and I'm then able to push it in the opposite direction and stop it from falling in the ditch. So, although I was always applying a force in this direction, it doesn't necessarily mean that the system was moving in that direction. So, how can we apply this to the wheel experiment? Well, we have to use something called the Coriolis force, or I'm going to use the Coriolis force. So basically, instead of thinking about this whole thing as one large system, what I'm going to do is I'm going to set up stuff called mass points, which is, instead of saying that centre of gravity is in the middle, I'm going to redefine that to be some discrete value of segments or mass points about the wheel circumference. So it's going to be many different parts about the wheel circumference, and I'm going to isolate one of those segments. Just check I'm on the right track. Yeah, so these can be called mass points, or rather in this, they could kind of be called pseudo-torques, but I'm not going to, that just seems a bit non-intuitive to understand what that pseudo-torque is. So, you guys remember what moments are? So, I'll just go over it again. A moment is, if we take a snapshot in time, what forces are acting on a system, where's it going, where's its position, what's it doing, that's a moment. So it's a snapshot in time. So, here's my wheel. I probably should have taped it up, but what I'll do is we're just going to focus on where this air plug gauge thing is. Right? So this is going to be one of our mass points, such that it's a number larger than 2. So we've divided the wheel into more than 2 parts. We'll say it's like 10, say. So it still has the same overall mass, it's just divided around the circumference. We're just focusing on this part. So we'll call this point moment 1. And we're going to ignore the precession that the gyroscope makes about the y-axis, about the string. And if we have a look at the moment, what we see is we have an acceleration, and we can put that direction facing this way. So we have an acceleration trying to move this mass point of the wheel downwards, right, about the x-axis. Then, so it has no velocity at the moment. It's just accelerating this way. If I then rotate 90 degrees, that's about 90 degrees, we'll call this point moment 2. And so moment 2, we now, because these mass points are infinitely small, we now don't actually have any acceleration in this direction. And we also don't have any acceleration in this direction. I'm sweating. So we have a net zero acceleration at this mass point, which is the same as moment 1. We're just, with respect to time, we've moved it. But now at moment 2, there's now no acceleration. So the way that we can think about this is there's been some velocity acting upon this segment as it goes from moment 1 to moment 2. So it's like the car's accelerating towards me, there's been some force applied in this direction. Oh, I can use my thing. Here we go. Right. So, right. We're now looking at this point. Actually, I'll use this. This will help reiterate. So, moment 2, there's no acceleration, but since there's been some velocity acting upon this thing, that's still going to be there, it hasn't been taken away. But if we continue to rotate another 90 degrees, we'll call this moment 3. So from moment 2, it had 0 acceleration. At moment 3, the wheel wants to move in this direction. It's an equal and opposite force to this point up here. So this point of the wheel wants to move in this direction. So there's a, equal and opposite acceleration in the opposite direction. But since acceleration was 0 here, and it's now over here, it means that there must have been some velocity pointing in this direction. So there was a velocity back up here from moment 1. So acceleration is pointing this way. There's no acceleration, which means that there must be a velocity this way. Then from here, its acceleration is 0. To here, acceleration is pointing this way. There must be a velocity pointing this way. Now, if we continue to rotate another 90 degrees, we're now at moment 4. There's now 0 acceleration again, because there was 0 acceleration here. There's no rotation laterally, which is what you might have seen. There's no rotation laterally at that point, at moment 4. And so we've had acceleration pointing this way. We now have no acceleration here, so there must have been some velocity pointing this way. Then from moment 4 back to new moment 5, which is going to be equal to moment 1. We've now made one full rotation. We're back at the top. We now are at the same place. So we have acceleration pointing this way with no velocity, but velocity has been pointing that way. So basically, we can define this as looking at where our 2 largest accelerations are, acceleration here, and rotate those vectors 90 degrees in the direction of rotation. And that's what we can kind of simplify the Coriolis force as. So let's try that out. We're going to rotate in this direction, which means that acceleration is pointing this way. The wheel should want to turn this direction, over and right. And there we go. So that's a brief kind of overview of the Coriolis force. Once again, if you have any questions, I have a whole PowerPoint backed up. So keep those in mind. I'm not going to go over any of the maths in this lecture, because it's not exactly going to help you guys understand what's actually going on in the system, because there's 2 ways that we can look at things. We can look at things through a maths perspective and a maths and physics perspective, using unit vectors and using torque and mass and things like that. But I don't really think that's going to push you guys over the line to understand what's actually happening here mathematically. So that's the reason why I'm not going to go into the maths, just going to confuse you guys further. And derivatives and stuff are different when you work with x and things. So, does anyone want to come up here and try this? Yeah, me too. Yeah. That's okay. So, there we go. I might just do a quick, sure. A quick example after you tried it. I'll see if the brief understanding of the Coriolis force.
Yeah, that sounds good.
Oh, let's do something. Just really want to do it.
Wait. That's when we're faster. Say 5, do this.
Get that tie in there. It only says.
Yeah, you can see it's trying to.
You put it on there.
itself. It didn't actually go up to the.
Yeah, right.
You can put it on an angle higher than 90 degrees.
That's what I was gonna say. What if I did? What?
Do you open it?
So do you think it would be reflection for
So it holds at the angle it's given.
Yeah.
That's cool.
So I don't really have much distance between the center of the system and the wheel. So the length of the rod, as I call it in the diagram, isn't really that long, so we're not going to be able to look at past the rod. But I don't think that was really important because we normally say that the mass of the rod is 0. It has no influence, so it's not really going to change things. Okay. Does anyone have any questions? Okay. I might go over an example just of seeing if you guys know what direction it's going to go in, and I'll try and pick up on any discrepancies that we have. So, if I have the wheel in this position and I rotate it like this, what direction is it going to process in? Yeah, so looking from the view at the top, anti-clockwise. Yeah. Right. What about the other direction? I wasn't looking at it. Whoop.
Oh wait.
No, it was clockwise. The other one, and then anti-clockwise.
Yeah, I mixed it up. Yeah, I did.
Oh, yeah, okay.
So it goes.
So doing that, like pulling
From
it down.
This should move this way.
It goes opposite of the way that you spin it from the top.
Yeah, I guess you can think of it like that.
Yeah, right.
Yeah. So, does anyone have any outstanding questions about either way that I've explained this? So, any questions about this? Yeah, sure.
When it's on an angle and it's spinning, does it slow down faster than if you just hold it yourself? So if I was to just hold it like this and spin it, would it slow down slower?
So it's not
Whereas
processing.
if it was in that position,
So it's not processing. Because if you hold it by both sides, it's only the torque induced that allows it to process about the y-axis. If there's no torque, if you're holding on to it, it's not going to process. So I can even take it off. And we can spin it up. I can hold it.
Oh.
But then, so there's force acting down, hard to demonstrate. Force acting downwards here, force acting upwards here, it's like a normal force. I'm now the string. And as soon as I stop that torque, it's going to stop. It's going to stop processing. And if I hold it up this side, see how it now goes in the opposite direction? Do you guys want to come up and try this? It's actually pretty fun. So hold it, just yeah, put your finger through.
Oh, yeah.
Once again, it's not levitating, you do have to hold on to it, but it feels like it's levitating. The wheel will also feel somewhat lighter in your hand.
I'm bad at it. And then the second you hold it at both things.
As soon as you're not allowing any torque in the system through some impulse, remember that's just a change in time. Change my notes. I didn't play a risk assessment. Oh, I said yeah.
Course handbrake.
No, that's my fault, not yours. Turns out they don't make these things for bike wheels. Yep.
Is it still rotating or on the x-axis?
When?
In both directions. When you spin it and it's rotating. And it's going around the y and it's there.
No, it does not. And if I went over the maths, oh, hold on. Let me try this out. So x-axis is that one. Not really. It kind of stays in the same plane. This part does not move.
In theory.
Yeah, yeah. I think if we go back into the deep space problem, there was no real width on this. It wouldn't change. But since we're in the real world, it has some length of this rod. This center point is technically changing about the XZ plane, so therefore you could kind of say it's rotating, if you look at it from a bird's eye view, because this part's going to be going like that, which means that it's rotating about. It's making some circular path in the XZ plane, but it's precessing about the y-axis. So, yeah. Anything else? Do we all feel confident deciding what direction the wheel's going to go given some rotation? Yeah? Alright, brilliant. That's the point of this lecture. Alright, great. I might just go over what this is. So this is my arts and crafts thing from yesterday. So basically, this is looking at the points of acceleration throughout our rotation. So this is the same as if we hold it up. Move this way. This part wants to move this way. This force is larger. Yeah, physically shown that. Nice. This acceleration is larger than these ones, and these ones are going to be somewhat equal as they change laterally from the y point. And lateral is just like against the y-axis. Yeah, any other questions? No? Alright, brilliant. Well, I have to go over that one. Alright, thank you very much for watching. I think that's it.